Okay, everybody, this is just a quick review lesson on solubility product, which is KSP, and molar solubility, and you know, defining both of those, and then how they kind of tie in with each other. And so this is 4-4, visible learning objective 4-4. But it's important to know when I say solubility product or KSP, you know what that is. And if I say molar solubility, you know what that is. They do, if you know one, you can calculate the other and vice versa. So if you know KSP, you could calculate molar solubility. If you know molar solubility, you can calculate KSP. There's other things you can calculate as well. And what kind of calculations you can do with the molar solubility. So once you know what the molar solubility of a compound is, what are the other kind of calculations you can make? All right, so let's jump into it. KSP and molar solubility. All right, so let's define some things first. So KSP is the solubility product for an ionic solid, okay? And what it really is it's equal to the equilibrium expression that shows 1 mole of an ionic solid dissolving in water. So we'll take our simplest form of an ionic solid, or our simplest example of an ionic solid, sodium chloride. So if I show solid sodium chloride yielding aqueous sodium ions and aqueous chloride ions, that chemical equation, it's not a chemical reaction, it's a physical change, not a chemical change, but this is a chemical equation. That particular chemical equation, the equilibrium constant expression for this reaction is equal to the KSP of that salt. So remember, we don't include solids in our expression, so KSP is always a product of the soluble ions, hence the name solubility product. So here's an ionic solid dissolving in water. The equilibrium constant K for this reaction is equal to the sodium ion concentration times the chloride concentration, and that is equal to KSP. And whatever that value is at a given temperature would be the KSP, or the solubility product for sodium chloride. Okay, so here's another example. All right, and it gets a little bit different when you don't have a 1-to-1 ratio of cation to anion. Here we have 3 aqueous ammonium ions and 1 phosphate ion. So if we wrote the equilibrium expression for this reaction, it would be the concentration of ammonium, but then we'd have to cube it times the concentration of phosphate. But the equilibrium constant K for this reaction is equal to the KSP for ammonium sulfate, okay? And so let's understand, it's always solid yielding aqueous ions. So the higher this value ends up being, the more ions you have in your solution, or the more this dissolves, right? And the lower this K value, whatever it is, the less this dissolves and the more the solid is favored. So really, what KSP tells you, it gives you a general idea of how soluble a compound is. The greater the KSP, the more it'll dissolve at that temperature. The smaller the value of KSP, the less it will dissolve at that temperature, right? The less favorable that process would be, okay? So again, if we look at our equilibrium, if we look at our KSP and it's something times 10 to the negative 20, we know that compound is, very insoluble. And if we looked up our solubility rules, it would probably tell us that compound is not considered to be soluble. But if the KSP was larger than that, then maybe that would be for a salt that is generally considered soluble in water. So I bet, sodium chloride has a pretty large KSP value compared to, let's say, silver chloride, because we know, based on solubility rules, sodium chloride is soluble and silver chloride is considered to be insoluble. So if we were to compare those KSP values, I'm sure that sodium chlorides would be larger than silver chlorides, all right? So again, it gives us KSP for an ionic solid, gives us a general idea of how soluble it is, all right? Now, what is molar solubility? Molar solubility is the molarity of a salt that the molarity of a salt when that salt is saturated in solution. So remember, saturated equals the dissolving process is at equilibrium. So saturated means equilibrium, okay? And whatever the molarity of the compound is when it's saturated, that is the molar solubility of the compound. It tells you molarity is moles per liter is it tells you how many moles of that compound you can dissolve in 1 liter to make a saturated solution. And again, that value would change as temperature changes, just like KSP would. So let's say the molar solubility of aluminum chloride is found to be this, okay, at 25 degrees Celsius. So that means that when this process reaches equilibrium, the molarity of aluminum chloride is 0.025. Or another way to say that is if you want to make a saturated solution of aluminum chloride, then you need to dissolve this many moles, 0.025 moles of this compound for every 1 liter of solution. And then if that's the case at 25 degrees Celsius, then that solution would be considered to be saturated and this process would have reached equilibrium. Okay? So if you're told the molar solubility of a compound is 0.025, then you know that that's the molarity of this compound when this equilibrium has been reached, right? Okay, so if 0.025 moles of aluminum chloride dissolve in 1 liter of solution to reach equilibrium, that means at equilibrium, the molarity of aluminum would be 0.025 and the molarity of chloride would be 0.075. Now let's understand how we found those, okay? Right? Remember, molar solubility is the molarity of the whole compound, but if 1 mole of this dissolves, you get 1 mole of aluminum, but you get 3 times the amount of chloride. So if you're given molar solubility of a compound, all you have to do is multiply that number by the subscript or the coefficient in the equation or the subscript of that ion in the formula to get the molarity of each individual ion. So I was told that the molar solubility of aluminum chloride at 25 degrees Celsius is 0.025 moles per liter. That means the molarity of aluminum at equilibrium would be 0.025 because it's a 1-to-1 ratio, but the molarity of chloride would be 3 times that because it's a 3-to-1 ratio. So notice we were given the molar solubility of a compound, but now we know the saturated concentrations or the equilibrium concentrations of each ion. So now we know the concentrations of each of those ions, and now we could plug those into the equilibrium expression and get the equilibrium constant. So now we plug in those equilibrium concentrations, which are the saturated concentrations, into the equilibrium expression. I know that for this reaction, KSP equals the concentration of aluminum times the concentration of chloride cubed, right? I don't have a denominator because that's a solid. So we plug those in. I plug in 0.025 here. I plug in 0.075 here. I got to remember to cube it, and I get my KSP. So what we want to understand is if we are given one of these values for a salt, for an ionic solid, we know all the values. So if you're given the molar solubility of the compound, then you can calculate the KSP. You can also calculate the molarity of the cation that you have in solution and at equilibrium, and you can calculate the equilibrium concentration of the anion. But also understand, given one of these values, you can calculate the other 3. So if you were just given the saturated concentration of the anion, you can figure out the cation using stoichiometry. You can figure out the molar solubility using stoichiometry. And then you can plug in these 2 values into the KSP expression to solve for the KSP. So given one of these things, you can find the others. Okay, it's very easy. You just got to know the difference between the 2, or the 4 different things, right? All right, so here's an example. I have a saturated solution of calcium hydroxide, and I was given the hydroxide concentration when it's saturated. So this is the equilibrium concentration of hydroxide. So how do we figure out the calcium? Well, there's 2 hydroxides for every 1 calcium. So if we just take this and divide it by 2, that's going to give us the concentration of calcium when it's saturated. So this is the concentration of hydroxide. That means 0.0025 would be the concentration of calcium. And notice the substrate for calcium is 1. So for every 1 mole of this compound, you get 1 mole of calcium. So not only is 0.0025 the molarity of calcium, it's also the molar solubility of the compound. it's also the molar solubility of the compound, because whatever the concentration is of the whole compound, whatever the concentration is of this whole compound, is the concentration of calcium, because it's a 1-to-1 ratio with calcium. So 0.005 molar is the hydroxide concentration. I can divide by 2 and get the calcium concentration, and I can also recognize that the calcium concentration and the molar solubility are going to be the same number. So that not only is the concentration of calcium, it's the molar solubility of the compound. Okay? But we can get the KSP, so we know that the KSP represents this equation. So this is the expression. We calculated those two molarities, or we were given that molarity. We calculated that one, plug them into the expression. Don't forget to square the hydroxide, and you get the KSP. So now we get the KSP for calcium hydroxide. And then again, the molar solubility of the compound is the same as the concentration of calcium, because it's a 1-to-1 ratio with calcium, and it's 1/2 the concentration of hydroxide, because it's a 1-to-2 ratio with hydroxide. So the molar solubility of the compound is that. All right. So again, given one thing, one of those things on this list, okay, let's go back up to this list. Given molar solubility of the compound, or given the KSP, or given the saturated molarity of a cation, or the saturated or equilibrium molarity of the anion, given one of those 4 things, we can solve for the other 3. Okay? All right. So what we're going to do is we're going to eventually figure out these KSP shortcuts, KSP molar solubility shortcuts. All right. So let's say we have an ionic compound where it's a 1-to-1 ratio of cation to anion, or anion to cation. And again, that should say ratio. And examples of this would be sodium chloride, magnesium oxide, aluminum nitride. They're all 1-to-1s. It doesn't matter what the charges are. This is +1, -1, but it's still a 1-to-1 ratio. +2, -2, still a 1-to-1 ratio. +3, -3, still a 1-to-1 ratio. If we made a Rice chart for this, a 1-to-1 ratio, it would always come up with the concentration of the cation is X, and the concentration of the anion is also X. They would be the same thing because they're a 1-to-1 ratio. And the KSP expression would always just equal the concentration of the cation times the concentration of the anion, and there would be no exponents. And since both of these would be considered the same value, X at equilibrium, you get KSP equals X squared. And because they're both 1-to-1 ratios with the compound AB, each ion, 1A for every 1AB, 1B minus for every 1AB, X in this chart would represent the molar solubility. It would represent the concentration of A plus at equilibrium. It would represent the concentration of B minus at equilibrium, but it would also represent the molar solubility of AB, okay? So if you set up a Rice chart for a KSP equation and you get your equilibrium concentrations in terms of X, and you plug that into the KSP expression, what X will represent is the molar solubility of the compound, and KSP is obviously the solubility product. So if you were given the KSP of AB, you could plug that in here, solve for X, and now you know the concentration of A plus, you know the concentration of B minus, and you know the molar solubility of the compound. X is the molar solubility of the compound, all right? So any salt with a 1-to-1 ratio, here's our shortcut where X is the molar solubility and KSP is the solubility product. So if I was given X, if I was given molar solubility, I could square it and that gives me the KSP. Or if I was given the KSP, I could take the square root and that'll give me the molar solubility, all right? But it's gonna be different when it's a different ratio. So now let's look at a compound that's a 1-to-2 or a 2-to-1 ratio. It doesn't matter if it's 1-to-2 cation to anion or 2-to-1 cation to anion. It's just a 1-to-2 ratio between ions. So here's one example, 1 calcium, 2 chlorides, 2 sodiums, 1 sulfate. So 2-to-1 or 1-to-2, doesn't matter. It would always follow this. If you made your Rice chart, the ion with a subscript of 2 would end up having a coefficient of 2, so that would be 2x in our Rice chart. But the one with the subscript of 1 would only be x. But if we plug them in to our, if we plugged in 2x here, we'd have 2x squared, which would end up being 4x squared, right? Because we got to square that. And then we'd have x plugged in here. So we get 2x squared times x, that simplifies to 4x cubed. So if you have this ratio, if your salt has this ratio, then this is the shortcut you follow, where KSP is the solubility product of the compound, and x is the molar solubility of the compound. So if we solve for x, X would be the concentration of B2 minus because it had a 1-to-1 ratio with a compound, but 2X would be the concentration of A plus at equilibrium, and X is still the concentration of the whole compound. So X is still the molar solubility in the shortcut. And in these KSP shortcuts, X is always the molar solubility of the compound. All right. So if you did this with every possibility of ratio of cation to anion, there's 4. You can have 1 to 2. Sorry, you can have 1 to 1. You could have 1 to 2. You could have 1 to 3 or 3 to 1, or you could have 2 to 3 or 3 to 2. Now, I guess there would be other you might have 1 to 4, and you might have other possible combinations, but these are kind of the classic ones. And when in doubt, you can just set up a Rice chart to figure it out. But if you just memorize these shortcuts for these different ratios, then that'll help you out. So it's a 1-to-1 ratio, KSP equals x squared, 1 to 2 ratio, KSP equals 4x cubed, 1 to 3 ratio, or 3 to 1, it doesn't matter, KSP equals 27x to the 4th, and if it's 2 to 3, it's going to be KSP equals 108x to the 5th, where KSP is the equilibrium constant or solubility product for the salt, and X is the molar solubility. So given molar solubility, you could solve for the KSP, or given the KSP, you could solve for the molar solubility of the compound. Okay, very quickly. And then once you know the molar solubility, you could take the molar solubility. Like once we solve for X here, then, you know, for this particular one, like let's go to this salt. If we solve for the, if we were given the KSP of calcium chloride and we solve for the molar solubility, the molar solubility times 1 would be the concentration of calcium, and the molar solubility times 2 would be the concentration of chloride. If it was this compound and we solved for X, the molar solubility, 2 times X would be the concentration of sodium, and 1 times X, 1 times the molar solubility, would be the concentration of sulfate. Okay? So learn those shortcuts. And let's do an example problem. So this is gonna, you know, if we can figure out the molar solubility, what's a calculation we can do with it? All right, so here's our example. Okay, it says what mass of lead chloride will dissolve in 5 liters of solution, okay, at 25 degrees Celsius if the KSP for lead chloride at 25 degrees Celsius is 1.8 times 10 to the negative 15. Now we already should know that lead chloride, lead 2 chloride is not very soluble. If we looked at our solubility rules, it would tell us it's an insoluble compound. And this right here, this KSP, it's so low, times 10 to the negative 15, you know, that's an indication that this compound is not very soluble. But we also have to understand that solubility isn't just black or white. It's not just will dissolve, won't dissolve. It's, you know, insoluble really means just a little bit will dissolve, and soluble means a lot of it will dissolve. So now we want to figure out exactly how much, all right? So the first thing I'm going to do is figure out the molar solubility of the compound. I was given KSP, so let's figure out the molar solubility. So shortcut, it's a 1 to 2 ratio. So we're following KSP equals 4x cubed. We're plugging in our KSP value and we're solving for X. X is the molar solubility of the compound. Okay. So the way you're going to do this is you're going to divide by 4 first and then take the cubed root. Okay. So let's say you were using this one. What you would do is if you were solving for X here, you would take your KSP value, divide by 108, and then take the 5th root. Here you would divide by 27 and take the 4th root. So don't take the 4th root and then divide and then take the 4th root. All right, so here we're going to divide by 4 and then take the cubed root. And so if we plug that into our calculator, we get X as 7.7 times 10 to the negative 6. Now remember, that's the molar solubility, that's moles per liter. So that's telling us to make a saturated solution of lead chloride in 1 liter, we need that many moles. We need 7.7 times 10 to the negative 6, not a big number, very small number. We need that many moles of lead chloride in 1 liter of solution, and it'll be saturated, okay? So that's how many moles for 1 liter of a saturated solution, but we wanted to know 5 liters. How many grams? We wanted to know mass. So now that we know how many moles per liter, we can take our volume of our solution and multiply by this. Liters will cancel out, and that'll give us how many moles of lead chloride we have, and then times the molar mass of lead chloride. So we would take our 5 liters, multiply it by our molar solubility, which is our concentration of that compound when it's saturated, okay, times the molar mass of lead chloride, and that would tell us how many grams. So not many, and so 0.011 grams, so it would only take 0.011 grams of lead chloride to saturate a 5 liter solution. So not a lot at all, okay? If you wanted to put it in 11 milligrams, right? 0.011 grams, 11 milligrams. So it would only take 11 milligrams to saturate 5 liters of solution for lead chloride. So that's how very, very, very slightly soluble it is. It's insoluble, but you know, this is why. It doesn't take much to saturate, okay? But also understand the other things we know, all right? The subscript for lead in the lead chloride is 1, so the molar solubility of the compound is the concentration of lead ions in a saturated solution. And for chloride, it would be double that. So if we took this and multiplied it by 2, that would be the chloride concentration, because the subscript of chloride in lead 2 chloride was 2. So if you take the molar solubility and you multiply it by the subscript of the ion, that gives you the concentration of the ion in a saturated solution. All right. So if you're asked for, like, you know, what mass of this will dissolve in this much solution, the key is find your molar solubility. The volume in liters times the molar solubility will give you how many moles of that compound will dissolve, and then multiply by the molar mass to get how many grams of that compound will dissolve. Okay? All right. So easy peasy. That's molar solubility in KSP. Not that big of a deal. Very simple stoichiometry. You just got to understand what they represent. Use your KSP shortcuts. And yeah, so not that difficult. You just got to remember, all KSPs don't have a denominator. People have been asking questions about like the bonus of the day and stuff like that. And it's been a KSP problem, and they're writing their K reaction or their K expression, and they still have that solid compound in the denominator. Remember, it's just the products for a KSP expression, just the ions, not the ionic solid itself. All right. So that's it. Have a good one.